All right, guys, I'm going to try and go through this as quickly as I can. This is the first video. I'll do questions 1 to 10. So we look at this guy. We've got velocity is proportional to t squared. Velocity is proportional to t squared. If you were to take the derivative of the velocity function, you would get an acceleration function, and f net is just m times a. So imagine taking the derivative of t squared to get a. That would be 2t. Remember, the coefficient becomes what the coefficient was before, which would be secretly a 1, times the old exponent, and then decrease your exponent by 1. Anyway, so it'd be 2t. It would be a linear function, like a straight line. So basically, that's what we're looking for. Since our acceleration function, which is what we get when we take the derivative, is just multiplied by mass, and it's a straight line, the answer is E. All right, let's take a look at this sucker. We got this frictionless system shown above, accelerated by an applied force of magnitude. The tension of the string between the blocks is... Dun, 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 dun. This isn't too bad. I mean, there's a couple ways you can look at this. A lot of the time, the way I think of it is this force is pulling everything, and everything's going to accelerate at the same rate because it's tied together. So kind of like, what fraction of the total force does this guy need to get so it all accelerates at the same rate? This is 1/3 the total mass, so it's going to need 1/3 the total force. So this is going to be 1/3 the total force. So that's one way of looking at it. If that kind of logical leap is a little rough for you, you can just straight do it mathy-wise. You can say, hey, my acceleration of the system, of everything together, is my total force divided by my total mass. And so my acceleration of the system is f over 3. And then if I want to find the f net on the 1 kilogram object, or let's make it a subscript, 1 kilogram, that's just going to equal m times a, which in this case is 1 kilogram. And the acceleration of this block is the same as the acceleration of the whole thing. So it's again f over 3 kilograms. And so we can get rid of our kilograms, and it's just 1/3 the total force. So either way you want to think about it. That's 2. Here we've got a 100 Newton weight suspended by 2 cords as shown below. And we want to know the tension in this slanted cord. Now, the key with this is just like grade 12 torque. Basically, this is the only thing pulling up on the object. So if you've got a 100 Newton object down, your up force has to equal your down force. Here's the only down force. Here's your only up force. It's 100 newtons. If we do 100 divided by sine 30, which is just a half, we'll get 200 newtons. Sine 30 is just a half. 100 divided by a half is 200 newtons. And so that would be this guy, 200 newtons. And there we are. Next one, number 4. We got a particle of mass m moving along a straight path with speed v defined by the function v equals bt squared plus c, where b and c are constants and t is time. What is the magnitude f of the net force in the particle at time t equals t1? So very much like how I was talking about solving this sucker, we're going to take the derivative of velocity with respect to time, which is acceleration. So if we do dv dt, we're taking the derivative of velocity with respect to time. Basically, it's going to be 2bt. That would be our acceleration. And f net is just ma, which would be equal to 2mbt1. Notice that t became t1 because we're looking for the net force in the particle at time t. Basically, This is how we solve for it at any time. And if we sub in t1 for t, we've got the fnet at time t1. So if it was like 5, we'd sub in 5 for t. So that's how you do that sucker. Yeah, number or E. And then for 5, we got to figure out which of these are realistic ways for a particle to find its instantaneous velocity and its acceleration and net force. Now, this isn't that bad. Things you got to note, your velocity is always tangent to your path. If you didn't have any force or acceleration, the object would just keep going in a straight line, and tangent to the path is kind of like what would be straight if you just let it free at that point. Acceleration and net force have to be in the same direction because Fnet equals m times a. So Fnet is pretty much acceleration times a scaling factor, which doesn't change its direction at all. And as we know from circular motion, if something's going to curve inward, it needs a net force and a net acceleration towards the center. So this guy doesn't work because A and F aren't in the same direction. V isn't tangent. This is just garbage. This is basically right, but it's got your acceleration and force and velocity reversed. If you swap them, that would be pretty good. The force is not in the opposite direction of the acceleration. That doesn't work at all, or the net force. D is it. D fits the bill. You've got, in general, a acceleration and velocity at least towards the center of the curve. With this year, we've mainly done situations where we've got constant speed circular motion. So it wasn't speeding up along its path. This has one component towards its center and one component in the direction of its path. So it'll go in sort of it'll curve, but it'll also be speeding up as it curves. And then this guy is just garbage. Basically, we just need to move the force down there. All right, number 6. We got 2 blocks pushed along a horizontal frictionless surface by a force of 20 newtons to the right. The force, we want to know the force that the 2 kilogram block exerts on the 3 kilogram block, which is the exact same because of Newton's third law. It's the same as the force the 3 kilogram block exerts on the 2 kilogram block. So kind of like, this is very, very similar to this guy. We need to figure out the overall acceleration and then figure out how much force this 3 kilogram guy has to push on the 2 kilogram guy. So it's going at the right acceleration. Because I just find it logically easier to think of the force the 3 kilogram pushes on the 2 kilogram. It's an easier conceptually way to solve than the force the 2 kilogram puts on the 3 kilogram, even though they're exact same magnitude. All right, so pretty easy. We've got 20 newtons and 5 kilograms. 20 divided by 5, A equals F divided by M, which in this case is 20 newtons divided by 5 kilograms. And this is for the whole system, but I mean, it's the same thing because they're all touching. So it's going at 4 meters per second squared. And so if this 2 kilogram guy is going to go at 4 meters per second squared, it's going to need a net force of 2 kilograms times 4 meters per second squared, which is just 8. And then we did all solve this by talking about the force the 3 kilogram would exert on the 2 kilogram, though of course that is not what the question is actually asking for. The magnitude is the same, but the direction is opposite. So it would be the 2 kilogram would push the 3 kilogram to the left. And that's it. All right, this guy is easy if you look at it the right way and much harder if you don't. This is actually one of the questions a lot of people tend to get wrong, even though if you look at it right, it's great. So we got a ball initially, it's initially going at the initial velocity and then it's hit by a stick, and then it's going with the final velocity there. And we want to know the direction of the average force on it. But as we talked about right here, the direction of the average force is the same as the direction of the acceleration. And one more step further, the direction of the acceleration is the direction of the change in velocity, because acceleration is just change in velocity over time, and dividing that by time does not change the direction. So we want to find the direction of the average force. That happens to be exactly the same as the direction of the acceleration, which is, again, exactly the same as the change in velocity. So all we do, usually the way I think about these guys is I start here. Keep in mind we're basically doing change in with vectors, and whether you're dealing with velocity or electric field strengths or displacement, it's all the same. So I always think of it in terms of displacement. So basically we start at this point, we end at this point. How do you get from the start to the end? Just like that, nice and easy. You could also do like delta V equals VF minus VI, which is the same as taking VF and then adding the opposite of VI. So this negative means just put the arrow on the other side, and then you can just add them tip to tail if you want, and you end up with the exact same thing. All right, so answer is B. All right, let's look at number 8. F1 is the magnitude of the force exerted by Earth on a satellite in orbit around Earth, and F2 is the magnitude of the force exerted by the satellite on the Earth, and which of the following is true? We're talking about two objects here. I push on you with 50 newtons. How hard do you push on me? It's exactly the same. Whether we're talking about gravity on two things, I pull on you with 50 newtons, you pull on me with 50 newtons. It's going to be exactly the same. Newton's third law is undefeated. So number C, or letter C. Number 9, we got 2.6 kilogram objects connected by a thread that passes over a light frictionless pulley, and we got a third object that's 0.3 kilograms there. We want to know the magnitude of the acceleration of the 0.3 kilogram object. Now that's great and all, but it's basically attached to a system. So really we want to find the acceleration of the system, which isn't that hard. We just use our handy dandy big minus small equals MA. That hokey formula I came up with, it's still useful. So our big force is just basically our total mass here is 0.9. So it's 0.9 times G times 9.8. Or in AP Physics, a lot of times we use 10 because that makes the math work out delightfully. And then minus 0.6 times 10. So this isn't left or right fighting. This is kind of one way for the thing to fall down versus the other. And that's going to equal our total mass, which in this case is 0.6 plus 0.6 plus 0.3, which is 1.5 times A. So we have a total force of 3 newtons equals 1.5 times A. So our acceleration is just 2 meters per second squared. And we are done. And then I'll maybe just do 11 here because these work together. And hopefully you can get these, but people make mistakes. It's fine. All right, so basically we just throw a ball and we're asking, hey, what's the acceleration at Q? The thing causing the acceleration is gravity. Gravity is pulling it down, so the force is down. That means the acceleration is down. If the net force is down, the acceleration is exactly the same way. I know it slows down, stops for an instant, but it never stops accelerating down. So the velocity goes to 0, at least vertically, at Q. The acceleration is not. It is always being pulled by gravity. And if it's being pulled by gravity, it's being accelerated. And which of the following best indicates the direction of the net force on the ball at point P? Again, assuming no air resistance, say air resistance is negligible, what are the forces acting on point P? Just gravity still. So again, even at point P, like its velocity is up at an angle, but the direction of the acceleration, the direction of the net force, is just, again, down. And that's it. Thanks for listening. Sorry for the